So, you see the right-hand side has an xy squared in this differential equation. So we will use Bernoulli's to do a transformation, okay? So let's say that. So Bernoulli transformation. Okay. What's the power on the y? The power is 2. So n equals 2. And the Bernoulli transformation demands that you let v, because as it is, you will not be able to solve it. Right. Okay, because of that y squared in there, which is a term that we didn't have on the other ones. So here we need to make that work, we need to use the Bernoulli equation in order to transform it into an equation in terms of v and y, v and x. We solve for v like we used to do, then we go back and we find y. Yeah. Okay, so the transformation demands that v equals y to the 1 minus n. Right? Am I correct? Let's verify that. Yeah. Okay. So that means this is equal y. N is 2. 1 minus 2. So this is y to the minus 1. So v is equal y to the minus 1. Okay. And now we will make the transformation in the differential equation. So we will replace y with y to the minus 1, except we also need y prime. So we will go and we will differentiate this. Right. Okay. So then dv over dx will be power rule on the y. So I'm differentiating this equation here. Yeah. Okay. So minus 1 y to the minus 2 times dy over dx. Because of the chain rule, you have to also differentiate y. Okay. And now we're going to plug all this back into the original differential equation. So you don't have to rely on formulas. You can just work this out from scratch. Yeah. Okay. So now substitute in, let's call this a. Okay. Substitute in a. So you will get, so okay, from here I can find y prime, right? What's y prime? Y prime is dy over dx. So I can solve this for y prime, and I get my y prime to be, just divide both sides by minus 1 y to the minus 2. So you get y prime to be minus y to the 2 dv over dx. Do you agree to that? I just divided this on the right hand side. 1 over y to the negative 2 is the same thing as y to the 2. And there's a minus sign. Okay.
Wait, so...
Yeah? I'm saying, if I divide here by y minus y to the minus 2 and here by minus y to the minus 2, this one goes away.
So n is basically, n is what?
N is the degree of the y.
Yeah.
When you put it in the standard form.
Right. Or it's 1.
So when you bring this up, it becomes minus y squared here. Okay? So when I substitute back into the differential equation, now I have into a, y prime is minus y squared dv over dx plus, what's y? We already said, oh, from here I could solve for y in terms of v. So from here I can say, just raise both of these to the minus 1. So y is equal to 1 over v. Do you agree? So then y becomes 1 over v, because the transformation necessitates that everything now goes from y to v. So this is 1 over v. No? Make sure. Yeah, okay. 1 over v equals x times y squared. So x times, And what's y squared? Well, if y is 1 over v, y squared is just 1 over v squared. Okay.
All right.
Now, also I can replace this y squared with 1 over v squared. So I might as well go ahead and do that. So 1 over v squared. And now I could multiply this entire differential equation by minus v squared, so I can put it in the standard form. So I will go ahead and multiply this whole thing by v squared, or minus v squared, since I have a minus here. So then this differential equation will reduce to dv over dx minus, if I multiply here by minus v squared, I get minus v equals minus x. Okay? Now, just move things around a little bit. Move this to the right-hand side. So dv over dx plus x equals, or actually, no, it was fine. It was fine. We don't need to do that. It's already in the standard form that we need it to be in. So, right? So now, this is a differential equation. You can test it for exactness. It won't be exact. So we'd have to use an integrating factor, and that becomes the previous section.
Right.
Okay? So now we will use
That's not good.
the integrating factor method.
Conductive liquids on a touch screen.
You know what I mean?
Yeah. It was writing.
Yeah. Was writing in small, yeah? In any event. So let's go ahead and do that. So integrating factor method. By the way, hint in the form of a question. If your differential equation is exact and you use an integrating factor, would that work?
No, you wouldn't. You wouldn't.
Well,
It
well, if that happens, you're just gonna get 1 for your integrating factor.
Yeah.
And it'll stay as is. So the integrating factor method is a pretty fair, safe method when you could use it.
Yeah.
Okay, so we're gonna multiply here by mu, here by mu, and here by mu.
Right.
Now keep in mind, v is taking the place of y here. Okay, so v is the dependent variable, x is the independent variable. Okay, and you can't help but realize that this is the product rule of v times mu.
Yeah.
Equals minus x mu. Fair enough?
Yeah.
So apply the product rule on this and you will get mu times dv over dx, which is this term right here, plus v times d mu over dx has to equal minus x mu. You understand? Now, this term is the same as this term here. So that means the middle terms have to be the same, which makes this has to equal to this, which means d mu over dx has to equal minus mu. Don't forget the minus sign, because there's a minus here. Separate the variables, so you get d mu over mu equals dx. And now do what? Integrate both sides. And we're going to get ln mu equals x, which means mu equals e to the x. So this is our integrating factor. And we're going to multiply our integrating factor into equation b here. Okay? So then b becomes d over dx of v times e to the x is equal to minus x e to the x. And unfortunately, we're going to run into one of those integration by parts another time in a second, as you can see from x e to the x. So now, let's move this dx over here, and we can integrate both sides. So the integral of the derivative will just get you that, you know, the inside. So you'll get v e to the x equals minus x e to the x, and plus c. Well, we haven't integrated yet. This will have to be integration by parts. Okay? So for integration by parts, let's do this in green. So the integral of vgu is equal to the integral of uv minus integral of, oops, I made a mistake, udv. udv equal uv minus the integral of vdu. Now don't confuse the Bernoulli's v with the integration by parts v. Those are two different things. Okay, so so for this one we will do integration by parts. So then u will equal x, which means du will equal dx, and dv will equal e to the x, which makes, or dx, which makes v equals e to the x. Okay, and now we will make the substitution. So then we get, so we will call this equation C. So now equation C becomes v e to the x is equal to, there's a minus sign here, and we will open a gate and carry the integration by parts inside the gate. So uv will be x e to the x minus the integral of v du will be the integral of e to the x dx, which will just be e to the x, because the integral of e to the x is just e to the x plus c. Okay? And now what we can do is divide everything by e to the x to get our v. So v is equal to minus, if you divide here by e to the x, you just get x. And if you divide here by e to the x, you just get 1. And this is just c over e to the x. Now, this is v. This is not yet y. So we need to go back and find y. Well, we've already said, now it's a straightforward algebra step, where we said y is 1 over v. So then, since y is equal to 1 over v, all we need to do is take the reciprocal of this, and that will be 1. So therefore, y equals 1 over minus x plus 1 plus c e to the minus x, because if you pull this up, it will be e to the minus x. And this would be the solution of our equation using Bernoulli's equation and making a Bernoulli transformation in the differential equation when it's in that format. Does that make sense? It's a bit long, but it's not that bad. There's just this extra step of introducing the transformation. And then you have to, of course, once you do the transformation, you have to take the derivative of v, because that's required for the derivative of y to be transformed into v
Yeah.
as a function of the derivative
Yeah,
of v.
V is the function to the one.
1 minus the degree of y.
Yeah.
Yeah, so it was 1 minus that.
Right.
So yeah, that does it. So we have a correction here, Ben. Let me tell you where things went.
Yeah.
So here there was a minus sign. So how about I'm just gonna put all this in thin, okay? So there was a minus sign here that we forgot. Okay, I forgot, which would make this a minus x, which would make this e to the minus x, okay, which would of course make when we multiply by the integrating factor e to the minus x, this will also become e to the minus x, and this is e to the minus x. So, and then this is e to the minus x right here, and this is e to the minus x. Okay, so when we do the integration by parts, we have u is x, so dv will be e to the minus x, which would make v minus e to the minus x, which would make this uv, which would make this here a minus v du, so this would be minus e to the minus x times dx, which would make this here, let's stay in, a plus. Okay, v du, yeah, which would make this a plus, and of course we have a minus sign here, we have a minus sign here, and we have a minus sign here. So far so good. 1 second, there's still a minus sign here, so if this is minus, this is going to become a plus. Okay, so then this turns out to be, oh, there's a minus sign here, so this is uv, which is minus x e to the minus x, minus v du, oh, which would make this, when you integrate it, a minus sign here, right? Because e to the minus x is minus e to the minus x, which would make this a minus here, okay? So, and then which would make this, we said e to the minus x. Yeah. And so now when you raise it up, when you do 1 over v, you're going to get, so minus x is plus x plus 1 plus ce. When you raise this up, it'll be ce to the x. So this minus sign correction just carries over. So the right answer, right? Because that happened right here on this minus sign. Changes the integrating factor. So the right answer is 1 over x plus 1 plus ce to the x. Okay. Any questions there?